I'm Wiebe Martin Winia, usually just known as Martin, or on the internet as QQWY, which is rather difficult to pronounce, but very easy to search for online. I'm currently working at the company Katerdesk, which is a Dutch startup building a software platform for auction houses, both to be able to manage their inventory, but more importantly also to hold live online auctions. And because of this, we get very sudden traffic spikes when an auction starts. And we need to handle that properly, and that is why Katerdesk is really trying to use and also build tools for maintainable and scalable software. This is also why Katerdesk is sponsoring part of my time maintaining the TypeCheck library. But what am I going to talk about today? First, what is type checking anyway, and why should you care for your Elixir application? After that, we will talk about the TypeCheck library itself, both its basic usage, what goes on under the hood, and what more advanced functionality the way it is built allows. And after that, I want to share some thoughts and dreams for the future. But first, let me address the elephant in the room. Jose had a wonderful keynote yesterday morning, and he surprised all of us, and especially me, by saying that he would like to add static types, set theoretic types to Elixir sometime in the future. And this might still take a couple of years. It's a research project for people who were not there yesterday morning's keynote. It might take a couple of years for that to get from the ground. Maybe it will never really get there, but at least there is now research going on into this. And I think this is a really exciting development. It did, however, mean that I had to spend some time yesterday evening, late at night, to update my slides a little bit. Although what I'm talking today can be considered very much complementary to the ideas that the Elixir core team has for the future. Because TypeCheck is something you can already use today, and you can very easily use in your existing applications using your existing Elixir type spec specifications. And it performs all the type checking at runtime rather than being a static tool. But let's take a step back and first talk about what is type checking anyway, just to make sure that everyone here is on the same page. Well, it makes sense to first define what exactly a type then is. And one nice intuitive way to think about types is to, for each of the values or named things in a program, say a type is the set of possibilities that this thing might have throughout the running time. One might consider number to be a type, and this is a quite general one. We can also have very specific types, say any color, as long as it is black. But this is also about as far as we can go with talking about this in general, and it's still rather vague. I believe many people are still joining the Zoom. Yes, it is still rather vague because, well, type checking is checking whether a particular value is one of these possibilities, but this is about as specific we can get with a definition, because how we use types in practice in our day-to-day lives very much depends on the particular programming language and other tooling that we are actually using. So generally speaking, we can subdivide programming languages into two groups. We have the dynamically typed programming languages and the statically typed ones. In dynamically typed languages, throughout the running time of our program, all of the named things, variables, parameters, etc., can take on many values of many different types throughout the whole running time. And this means that whenever we try to perform a particular operation, then at the very last moment, the Elixir runtime, or the runtime of whatever language you use, has to check, wait, is this operation actually permitted or not? As a simple example, here's some Elixir code. This is a function taking two parameters, a and b, and somewhere in the middle we calculate a minus b. Now this is fine if a and b are numbers, but the runtime will have to check just before executing a minus b, wait, are a and b actually numbers? Or maybe right now one of them is a string, as an example. And if one of them is not a number, well, then we have a problem, and in many languages, this is resolved by raising some kind of exception at runtime. Now, statically typed languages are very different, because in statically typed languages, all the named things in a program only ever can be of a single type throughout the whole running time. And we have to know this type beforehand. And usually this means explicitly annotating all the various things in a program to show what we intend the type to be. Now, here is the same function again. This is Rust syntax. It does the same thing. Again, we calculate a minus b. However, now we are explicitly saying that actually, when this function is called, we expect a to be an integer and b to also be an integer. And the interesting thing about this approach is now, at the very latest, we know that we're doing something wrong over here when we call the function, rather than the software breaking only somewhere in the middle, because we already know here whether we are using the function correctly or not. So this is a bit of an interesting trade-off. These are two very different ways of thinking about software. And a question, of course, is it worth it to be slightly more explicit, but be able to be notified earlier about problems, or be more like finding out the root cause of a problem rather than the immediate thing? Because rather than being interested in error, I cannot subtract a string from a number, we're interested in why b, for instance, is not a number in the first place. And it might be originating somewhere completely else in our code base. So, of course, the answer to this question, when should you use one or the other, is, well, it depends. However, the main reason, in my opinion, to use some statically typed features in our day-to-day life is to allow for more maintainable code. And Jose gave a lot of examples and other trade-offs yesterday in his keynote. And another thing that goes into much more detail about this is Sasha Jurich's talk of ElixirConf of 2021, where he talks about how to keep Elixir code maintainable. And one of the things he specifies in there is also using Elixir's type spec syntax, which we will cover later on in this talk. But this divide in two categories, either you pick dynamic or static, is no longer really the case. Like in practice, many languages are somewhere on this sliding scale. And nowadays, it even is the case that statically typed languages have received quite a number of more dynamic features, and dynamically typed languages have received a number of statically typed features. And the nice thing about this is that you can really mix and match, rather than picking at the beginning of your project which language you use. You can really specify on a situation-by-situation basis, wait, do I really want to use everything dynamically here, or maybe I want to add some static checks, or the other way around? So that's really powerful. But that's enough talk in general. Now let's look at Elixir specifically. Elixir inherits a lot of its way about dealing with values and types from Erlang, which itself takes a lot of inspiration from Prolog. And all of these three, therefore, are very dynamically typed languages. However, Erlang and Elixir do ship with two features that you can use to add some static checking to your code: type specs and dialyzer. So the type specification syntax is a way to specify for each of your functions what you expect the input types to be, as well as the output result. And the nice thing is that it's a very clear and concise way to convey how you expect the function to be used. However, it also has some disadvantages. By default, it really is only used as part of your documentation. And another problem is that some common types that we regularly use in Elixir are not supported by the syntax. For instance, string constants cannot be used as singleton types in the type spec syntax. And when we're writing Elixir code, for instance, a Phoenix controller or a live view gen server, then it would be really useful if we were to be able to specify the type of the input parameters that we expect for particular functions. Another thing we very frequently use in Elixir is protocols and implementing protocols for various types. But in the type spec syntax, the best it can do is tell you, well, this might be anything, because we don't know yet what particular types actually end up implementing a particular protocol, at least statically. And finally, it might be very common, or rather, from time to time, it is really worth it to think about data structures where you have your own rules and things you want to be true when the data structure is constructed. And there's no way to specify this in the type spec syntax either. So, for instance, if we're talking about the decimal library, there's no real way to make sure, using the type spec syntax that we have today, to specify whether a particular decimal struct is valid or not. Now, Dialyzer builds on top of the type spec syntax to add a couple of extra guarantees, and that's really nice. For instance, it can use the type specs to check whether the implementation of your various functions conforms with the spec that you wrote down. And this helps to find some common mistakes. And it is able to run this statically, that is, without executing your whole code base. So that's really nice. So that really prevents your specifications and the implementations of your functions diverging over time. However, Dialyzer also has quite a number of drawbacks. For instance, there are some common mistakes which, at least by default, it is unable to find. And also, there are some situations where your code is actually okay, but it will complain about it. And finally, Dialyzer is not really known to be very fast, especially for larger code bases. And when it does complain about something, it might be rather difficult to figure out what is going wrong, and even more difficult, what you should do to resolve it. So because of these reasons, and also because it was introduced much later to Erlang, it is opt-in. And that also means that by default, it's not used in projects, and there are many libraries out there which you might be using as a dependency that are not using Dialyzer, and then again, you might see diverging implementations from specifications in those dependencies, and then Dialyzer might warn in your project about problems in your dependencies. And maybe this is what you want, but maybe it might mainly confuse you. As a side note, there now is a new project called Gradualizer, which tries to fix some of these shortcomings of Dialyzer, and is very worth checking out. However, currently it's still in an early experimental stage, but definitely keep your eye on that. But clearly, while type specs and Dialyzer are very powerful and useful, and you definitely should use them, or at least try whether you like to use them in your code, they have very clear limitations. And not everything that we would like to write in the type specs can be specified, and more powerful things that we might want to express cannot be specified even if you were to try really, really hard, and could not ever be checked statically in either case. Not even by the cool tools which Jose and the Elixir core team currently are thinking about in theory. And finally, when there's a problem, it would be really nice if the error that you receive as a user is clear enough for you to just be able to fix the problem. So this is why I started thinking about some alternative approach. Is it possible? Is there another approach to typing, to add checking to your Elixir code? And the answer, of course, is yes. But to get there, I first want to sidestep and introduce a new concept to you: function contracts. And maybe you've heard about this already before, or maybe it's very, very new to you, but probably you're already aware, at least subconsciously, about this, but it might not have you might not have known about it explicitly yet. Because every time we are using code, and it's not one big file, but rather split up in multiple different functions, then every time we call a function, that function has certain expectations, both about the general state of the world and the particular parameters that it accepts as input. If those expectations are met, it can do its work successfully. And then when it returns, we as caller also have certain expectations about the result that is returned. And this is not something that you have in some places and not elsewhere. It's always there. It's a property of the underlying algorithm which you are implementing. However, how visible it is, so how explicit you are able to see it and understand it as a developer, very much differs by the way the function has been implemented. But if it is explicit, or also, by the way, just in general, if one of these contracts breaks, then it is a very clear indication that something is wrong. Like, you cannot use this to fix all bugs or something crazy like that, but if a contract breaks, then that is a symptom of a bug somewhere. And this again brings me back to my point of clarity, where splitting functions up this way both makes it more explicit what the individual functions do, but also gives us this early warning system about certain kinds of bugs that might be lurking in our code base. So if this is still a bit vague gobbledygook to you, let me show you a nice example with Elixir code about how Clarity can improve and how we can add some checks, a real contract to a function to make it really explicit. Here we have a module called foo with a function bar, and we have a parameter a and b, and it's really, really unclear what's going on here. It might be anything. But if we use some more descriptive naming, then we can see that we're calculating some kind of top 10 here of high scores. And it's even more clear if we actually use descriptive naming for the parameters as well. Clearly, users is some kind of collection, scoring fun is probably some kind of function, and there's a lot of code out there that looks like this, but it's even more common to add this type spec, and now we can already clearly see that, hey, users should always be a list of user structs, and scoring fun is a function taking a single user and returning a float. And with all of this, we will always be able to return a new list of users. But you could go a step further than this, and especially in library code, many people do, or also if your main application is split up into multiple concrete sections, multiple boundaries. And the tools for this are already baked in Elixir. Pattern matching and maybe some guard tests here and there. So in this case, we could check, is users indeed a list? And is this function indeed a function taking a single argument? And this is about as far as most code goes. And it's nice, we have some checks at runtime. So when people try things out in IEX or also in a live production environment, we are able to check some basic problems. However, we're not checking whether the various user structs are indeed correct, or whether this function that is passed in indeed is correct, or whether this function as a general always returns a list of users. And that would be really, really useful. On the other hand, already we have a problem here. There is duplication, and I will get back to this. And it's not immediately obvious to most people what is going wrong here, but I will get back to it. But we might make the checks more explicit by going one step further manually and write something that looks like this. Now we're able to check all the user structs that are passed in the list, but no longer can we do it as a pattern match, so we have to extract it in some kind of helper function, and well, what exactly do we want to raise anyway when there's a problem? And also, how do we check if this function that is passed in itself actually works correctly? It's rather tricky to write this. So most people don't go this far, and also this code is not really idiomatic Elixir anymore. It's really difficult to see where does the contract checking end, where does the actual implementation of the function begin, and that's horrible. But also already on the previous slide we had duplication, and it might be even more obvious here. In any case, there are three problems here. The errors are often just some ad hoc thing which somebody typed in, or maybe it's just an argument error or function clause error. And more difficult checks are not done at all, as just explained, because how do we check this function anyway? And finally, we're duplicating code. We are writing the same contract twice, once in the type specification syntax and once more in normal Elixir syntax with pattern matching and guard clauses. And that is a shame, and that is again a way where the specification and the implementation might slightly diverge over time, and it just is extra boilerplate. And this is where the type check library comes in. Because just by going back to the version where we only wrote out the spec, but now adding use type check to the top of a module, we get essentially the same as what we wrote by hand, but then even better, even more powerful. Because now, by adding this use type check and changing the normal add spec to add spec exclamation point, type check will generate a runtime wrapper around this function to check both its input as well as when the function has finished, check its output. And when there are errors, it will do its best to display these errors in a format which is very understandable to the user. We will see some examples in a couple of slides. And finally, it will also generate difficult checks, and it will still also output the original spec, so Dialyzer will still be able to use your code, and it will also still show up in documentation. And this is why I named my talk Effortless, because the only thing you need to do is add this use type check, and in the places where you want to change the normal spec for spec exclamation point. So you can very easily add this to your existing code base. So this is what's going on behind the scenes. We have this code, and then when this module is compiled, it expands to the following. So we get the original spec, so dialyzer still works, documentation still works, and then we have the original code that you wrote, but then the extra code that it gets inserted into your module is the def overridable of your original function, and we override it with an implementation that checks the various parameters, calls the original thing, and checks the result. And finally, we also add the types and specs themselves, a representation as structs, and that can be very useful for certain kinds of reflection, metaprogramming, and also specification testing, which I will get back to later on in this talk. As a final note, here I've shown this a little bit as pseudocode, because in practice, all of the various type checks are compiled fully in line, and then it would no longer fit on the slide. But the advantage of compiling stuff in line means that the Erlang compiler is really able to optimize any redundancy away in there, and also redundancy between the checks and certain kinds of pattern matching, which you might do in your own function as well. So you might have the question, how readable are the error messages which you get from type check? Well, here's an example of this top 10 function, which we were using as before on the last couple of slides. When we pass this a couple of numbers, then type check will complain the call failed because parameter 1 is not the list of users, rather it's the value 1. And then it goes down into more detail, showing, breaking down what exactly the problem is. And this is really useful, especially if the input to your function gets larger. Say you have a nested structs or nested structs containing lists, containing structs, containing lists, etc. So here, for an example, we do pass in a list with a user object, but actually it's still not valid, because it turns out the first parameter is not valid, because the first element of the list is not valid, because the H key is nil, but it should be an integer. And this way, it becomes very clear to people using your library or your code, or maybe you are implementing an API and you can add types for that as well, what they should change in their input, why it is incorrect. And finally, I want to show you here, type check is checking the function which is passed in and says, well, actually, if we call the function, then the result that it returns is not the float, which it should be, but rather, in this case, the string A. Now, if this is really easy to get started with your existing code, but if you want more fine-grained control about the types or more detail, then you can use some extensions which TypeCheck supports on top of the original TypeSpec syntax. So we can use ranges for floats, we can use list literals, for instance, we can have those parameter maps for Phoenix controllers, and we can use we can check whether a data structure that is passed implements a particular protocol or not. And if you want to do anything else, you can use arbitrary Elixir code in so-called type guards. Another question you might have is this fast enough? And the short answer is yes, probably, because the checks that it does scale with the size of your input. So for constants like numbers, atoms, strings, it will be a constant time. If you pass in a list or a map, it will be as slow as the number, like it will slow down with the amount of elements inside of that collection. And if you really need to, you can turn it off, on and off in a very granular way at compile time. And what's really nice, in OTP 25, the Erlang OTP team added a lot more optimizations while compiling your code, and TypeCheck, the kind of inline code that TypeCheck creates, works very well with this. So I still need to do more benchmarks, and that is definitely on the roadmap for TypeCheck. But for instance, the test suite of TypeCheck itself saw a roughly 30% increase in speed when switching from OTP 24 to 25. Now let's talk about some more advanced functionality that TypeCheck provides. Besides specifying your individual functions, you can also use typecheck.conforms within a particular piece of code. And this is, for instance, very useful when you're implementing an API and you want to check against a variable which originates from a user. And then you can also do more programmatic manipulation of the resulting error struct, which TypeCheck returns. And you can also customize formatters. By default, our formatter uses Elixir-specific terms, but maybe if you're returning JSON to some users, you might want to use JSON-specific terms. Another thing I want to go into more detail about today is spec testing, which is a very powerful feature, which the reflection stuff I showed earlier allows for. Spec testing or specification testing is a really simple way with no boilerplate whatsoever to add property-based testing to your Elixir code. One could say it is a gateway drug into property-based testing, if you will. And the idea is that if we have the spec for a function, we have specified what valid sets of input parameters should be. And now we can turn that into a property-based testing generator, so we can just generate as many sets of valid input parameters as we want. And that way we can get more confidence in that our function indeed is working correctly. So here's an example. Here we have a rating struct with a value and an author, and then we have a spec here to calculate the average rating. So it takes a list, it extracts all the values from the value key, and then it sums them and divides by the number of elements in the list. Now, this is really nice code, and if we now want to spec test this, we just, in the test module, add spec test rating. And if the syntax looks familiar to you, yes, it is very similar to doctest. It also allows for much of the same options that doctest allows. By default, it will use all of the specs that have exclamation points behind them in your original module to add these automated property-based tests for them. So in this example, we will generate many different lists of rating structs and call this function and check, does it return a number or does it crash and break somewhere in the middle? And actually, when we try to run this code, very quickly we get an error. Text is a little bit small, so maybe it's difficult to see. But the error here is that, well, actually, if you pass this an empty list, we end up dividing by 0. And depending on how well-versed you are, maybe this was not immediately obvious to you from the code on the previous slide. But this is a really nice way to get very quick feedback about some level of confidence, some level of resilience of your code. And it's very easy to change after you know these kind of edge cases. And also, if those specification tests are not enough, then you can always just use those types as a starting point, because you can turn them into property-based testing generators, and then you can add your own setup and cleanup logic around it, for instance, and write your own property-based tests for them. But spec tests are a very simple way to get started. If you want to know more about property-based testing, these are 2 resources which I very much recommend. Now, a final question that you might have is, you have all built all these nice tools about type checking at runtime, adding specification testing, having a nice formatter, but how well does it all work in practice? How resilient is type check itself? Well, wouldn't it be nice to be able to use those type checks and those specification tests to type check? And this is rather difficult, because if you try to do this, then the Elixir compiler will complain at you and say you're trying to build a circular dependency here. But there is a way to get this working, and this is exactly what I did. We first compile all the modules that contain the built-in type definitions. After that, we compile all the code that depends on those type definitions to build the nice syntactic sugar on top. And once we have the syntactic sugar, we recompile everything, but now we can use the syntactic sugar at the module level of our original type definition modules. And this way, TypeCheck's documentation contains all this information about TypeCheck itself, and all of the error results that are returned, all of the internal data types of the formatter, everything is type-checked and everything is spec-tested as well. And curiously enough, this also means that when you use type-check at compile time for your module and you're configuring it wrong, or you are building a type that doesn't make any sense because you are slightly misusing the type specification syntax, then you will get errors. And they will have exactly the same nice formatted error messages as type-check uses elsewhere. But it's at the compile time for your module, but TypeCheck doesn't care because it itself is already compiled. If this is going a bit too far for you, don't worry. I'm finished with all the crazy meta-programming stuff. The next thing I want to talk about is some ideas for the future. Currently, we're at version 0.12, and we're very, very close to a stable release, so that will probably happen later this summer. And after the stable release, I hope to provide some number of companion libraries for commonly used other Elixir libraries like Phoenix, Ecto, Yason, Decimal, etc., to be easy to integrate better with all of that ecosystem. But currently, TypeCheck already supports all of the types that are built in Elixir, both the built-in types as well as all the types of all the various modules that Elixir itself ships with. And it is also very easy to add your own types for modules, both your own modules, but also dependencies that you might be using. Now, I want to do thorough benchmarking of all the particular checks which are generated and improve the efficiency of those checks further. And the nice thing about that is that if you're using TypeCheck, then if there's a new version and you update it, then your code will magically get faster, and that would be really nice. And finally, something I would really like to do is to add support also for Proper. Currently, we support stream data, but Proper is another property-based testing library that also allows for stateful property-based testing, and it would be really, really cool if TypeCheck could also be used in those kind of property-based tests as well. Now, help with all of these features is very much appreciated, and also, of course, feedback in general. But to conclude, type checks in general and type annotations are a really powerful tool to improve the code resilience and the clarity maintainability of your code. And TypeCheck, the library, is a way to very effortlessly get started with some type checking in your existing Elixir code bases. And it is out now. You can already use it right now. So please try it out, and I would love to hear your feedback. So that's it for me. Thank you very much for listening, and I would love to answer your questions. Thank you.
Any questions? Yep.
Thank you. Is the spec test part of the TypeCheck library, or something that can be used standalone, even to spec test or based on the standard specs?
Spec test is part of the library and very much depends on those type structs having been built. Although it is not that difficult. So like the spec test functionality itself is a small bit of extra stuff on top. So maybe it could be extracted as well to something separate if you'd like. But you can also use the spec testing with your existing types and just not use the runtime type checking part, because you can turn it off per environment. So maybe you only want, you do want the runtime checks in development, but not in production. But also per OTP app, per module, per function, or you could have at compile time some extra crazy logic you'd like to finally decide whether you want to turn it on or not, on or off in a particular place.
We've got a question from Jiang Ji. Hopefully you can unmute yourself.
Hi. Can you hear me?
Yes.
So in our code base, we actually have a ton of errors in the type stacks, and we tried to turn on Dialyzer, which didn't go well because it produced thousands of errors. So I've been thinking whether we can use TypeCheck to actually deal with those errors. For example, we can turn it on in the dev environment and test environment, and it should give error messages already.
Yes, exactly. And that would be a very easy way to get some quick results and get some ideas about things that your code is currently brittle. Yes. Yes, it's a very good idea to try that out. And because it's so easy to add TypeCheck to your existing code base, you don't have to rewrite everything. You can just add it to a single module and you do a couple of tests there and try it out. And if it doesn't work, you can very easily revert it because there's just not much work to do to use it. So I think it's a very good approach to try that if you have troubles understanding why Dialyzer is mad at you.
Sounds great. Thanks.
Hello.
Yeah. So firstly, thanks for the talk. Really looking forward to try it out. And I wanted to ask whether it's backwards compatible in regards to dialyzers, so that I can run dialyzer on the specs with the exclamation mark.
Yes, yes. It still, at compile time, creates the original spec. So you can still use dialyzer alongside type check. And if you use those type extensions, so the extensions to things that are not allowed in normal type specifications, then those will be removed. The types will be made more general. Yeah, so if, for instance, if you have a float literal in one of your things that you want to check at runtime, then it will be transformed for in documentation and dialyzer to just be the type float, parentheses open, parentheses close. Because that is the most granular that dialyzer understands for this particular example.